exaggerated situation. Now, truthfully, from the mathematical perspective, most of our planetary orbits are only slightly elliptical. Other things, such as comets, are highly elliptical, and they still obey Kepler's laws. Planets sweep out equal area in equal time. And in fact, that isn't a statement of momentum again. That was an observation. And Kepler did precede Newton by a generation or two. So you've got an early Newtonian type discovery here. But the mathematical expression that typically is associated with Kepler's laws is the third law. And it basically says, and you'll see it written in some other forms, that the ratio of the periods squared is equal to the ratio of the semi-major axes cubed. When we say a semi-major axis, that actually is this distance right here. That's an S. For most planets, that's pretty close to the orbital radius because it's very close to a circle. Kepler's third law is still often used, even though it's significantly dated. It's still often used for an approximation when we're looking, especially in an extraplanetary situation, when we're looking at exoplanets and so on, to see if there's an additional planet. Newton's law of universal gravity is a much more mathematical situation. While it is still a straightforward presentation, you can actually go read through some of the logical arguments that were made. But what Newton observed was that the force of attraction between any two objects is going to be inversely related to the square of the distance between their centers and directly related to the product of masses. And if we look at this, what we know is forces should be in terms of newtons, which are kilogram meter squared per second squared. The unit for G is going to have to give us something that would leave us with a kilogram in the numerator, and we know we're multiplying the two masses, so that means we're going to have a kilogram in the denominator, and then we're going to have a meters at the top. Okay, what we end up with basically is a Newton meter squared per kilogram squared. Ceres, the largest asteroid in our solar system, has a spherical body with a mass of 6,000 times less than the Earth's and a radius which is 13 times smaller. If an astronaut weighs 400 newtons on Earth, what is her weight on Ceres? Well, so we know that for the Earth, weight is mg. Well, this is the same thing as big G, m1, m2 over r squared, where this is the radius of the Earth. We can say this is the mass of the Earth, and this is the mass of the astronaut. Her mass is not going to change, and big G is not going to change. So her weight on Ceres, since this equals 400 newtons, excuse me, her weight on Ceres is going to be big G times her mass times the mass of Ceres divided by the radius of Ceres squared. Well, we know that the mass of Ceres is 6,000 times less than the Earth. So, mass of Ceres is equal to the mass of the Earth divided by 6,000. We also know that the radius of Ceres is the radius of the Earth divided by 13. So we can do a little bit of substitution here. Big G, mass of the astronaut, mass of Ceres, which we can write as me over 6,000. The radius of Ceres, which we can write as re over 13 squared. Big G, ma, me over 6,000 divided by re squared over 169, which is 13 squared. Well, the big G, mass of the astronaut, mass of the Earth, over the radius of the Earth squared is what we would have looking at just this numerator. times 169 over 6,000. This is 400, not 406. It's 400 newtons. So that means her weight on Ceres is going to be approximately 11.3 newtons. And using the same idea, how high above the Earth's surface must a rocket be in order to have 1/100th or 1% the weight it would have at the surface? Okay, so what we know again is that the weight on the surface is equal to big G, mass of the rocket, mass of the Earth over the radius of the Earth squared. Now we need to know 1% of the weight. Mass of the rocket, mass of the Earth over radius of the Earth plus some height, h. I'm going to multiply out this denominator, radius of the Earth squared plus 2 times radius of the Earth times the height plus the height squared. If I then get this by itself, radius of the Earth squared plus 2 times radius of the Earth height plus the height squared is equal to 100 big G, mass of the rocket, mass of the Earth over the weight. I can now solve. Actually, it would probably have been easier just to have left this as the radius of the Earth plus the height squared is equal to 100 big G, mass of the rocket, mass of the Earth over the weight of the rocket. Well, all that's going to be is what? All that the big G M R M E over FW is just the radius of the Earth squared. So that means that the radius of the Earth plus h squared is equal to 100 times the radius of the Earth squared. If I take the square root, that means the radius of the Earth plus h is equal to plus or minus 10 times the radius of the Earth. If I solve this, I either get the radius of the Earth is equal to 9 times the radius of the Earth, excuse me, the height is equal to 9 times the radius of the Earth, or the height is equal to negative 11 times the radius of the Earth. Well, why are there two answers? Well, mathematically, obviously, we have the square term here. But if we think about why we have two answers from the Earth's perspective, if this is the radius of the Earth, and then this is 9 times that height, if we're looking at it from the other side of the Earth, 9, 10, 11. So from the other side of the Earth, it's 11 radii away. Now this one I'm going to leave as an exercise to the student. If you have questions, be sure you ask on this.